Thanks. Hello, everybody. Before starting my talk, I want to say something. Today, I heard a really sad news. My high school mathematics teacher, Sanjay Pahadi, he is no longer with us. I'm really sad because of that. His tragic demise at an early age shocked me. He was a friend, philosopher, and guide to his students, and he has a big influence in, in my career choice I made, studying mathematics. May his soul rest in peace. So I'm going to dedicate this talk to him. Okay, so I'm going to talk about maximum number of cliques in a graph with bounded maximum degree. Right, that's the title of my talk. So let me first briefly tell you what two-run problem is. I'm sure all of you have seen this. So in two-run problem, we ask to maximize number of edges in an n vertex F free graph. So F is some fixed graph, and in the generalized two-run problem, we just maximize number of copies of general graph instead of maximizing number of edges. Okay, so my talk will be about this generalized two-run problem when H is a clique with T vertices and F is a star graph K1 comma delta plus 1. This is just you have this, you have delta plus 1 many leaves, okay, and of course K1 comma delta plus 1 free, this condition is same as maximum degree at most delta. Okay, so the question is to maximize number of copies of KT in a graph with whose maximum degree is at most delta, and the number of vertices is fixed. I didn't realize. So what is a natural guess? So let me actually write the problem. So question is maximize number of copies of KT in an n vertex graph whose maximum degree is at most delta. Okay, anyway, so if you think about t equals to 3, a natural guess would be why don't we have as large cliques as possible? The largest clique you can have is k delta plus 1 because the maximum degree is bounded by delta. So you have bunch of them, and then at the end with the remaining vertices you have a small clique, right? So this would be a natural guess, but when you have t equals to 2, that's not true. You can have a delta regular graph, right? So that would be clearly better than this. right? Anyway, when r is 0 and t is greater equals to 3, you can check that this construction is actually the best you can do, like unique best. So basically you don't have this like residual part. So let me tell you what is known, or like what has been done. Oh, right. I should write. So we have like n vertex. So we'll assume that n is of the form q times delta plus 1 plus r, where r is something between 0 and delta, and everything is integer, obviously. So let's start with known results. So Cutler and Radcliffe in 2014, they proved the following: for all n vertex graph G with max degree at most delta. So throughout n is this. Okay, I'm not going to specify. Then the number of complete subgraphs of G is at most like the number of complete subgraphs of this construction, which I'm going to denote by q times k delta plus 1 union k. Okay, let me actually define what this k means explicitly. So notation. So ktg means number of copies of kt in G, and kg means summation t greater equals to 2 ktg. So basically the total number of cliques you have in your graph whose size is at least 2. Okay? So they proved that so if you count all the cliques of order at least 2, this is the best you can do. Okay, that was nice. So we still have like all these conditions into play. Everything all right? So the next result we have is by Gan, Low, Sudakov. So it was in 2015. They have two results. They resolved the case when q is 1 and t is 3, and they proved basically this is basically the best you can do. And second, let me write, why not? So k3g this equals to k3 k delta plus 1 union kr. And remember, in this case n is just delta plus 1 plus r because q is 1. And secondly, he proved that if you so he basically reduced the general problem of generality to the case t equals to 3. So he proved the following: for all n vertex G with now, if you can prove that k3g less equals to k3 q k delta plus 1 union kr, if you can prove this, that is equivalent to proving like everything same here, ktg less equals to kt for all t greater equals to 3. So he basically reduced the general problem to the case t equals to 3. And finally in 2020, Chase proved that. So Chase is a PhD student of Ben Green. He proved that this K3G is indeed less equals to K. He basically proved this K3Q K delta plus 1 union KR. So now if you combine these two results, basically you know that this is the best you can do. So this was like, you know, the series of results. I'm sorry? Good question, very good question. So the equality essentially holds for this. But there are some, like, you know, cases for which this is not unique. If you consider t equals to 3, r equals to 2. So what happens to this residual piece? You have two vertices, right? So it doesn't matter if you put an edge between them or not, right? So essentially, because of this kind of reason, you sometimes don't have uniqueness. Otherwise, like, you know, like you always have this, like, you know, union of k delta plus 1. Okay? Yeah, that is true. If R is at least T, then this is the unique structure. Yes, that is correct.
So, am I understanding correctly that the second result of Gan law Sudakov is to show that
so
it's true for T, then it's true for every T?
Every T, yes, that is correct.
And Chase's theorem is true.
It's true for 3 basically, the proof. So this proof and this implication, like, you know, the reduction to t equals to 3 case, they are very different proofs actually. So this proof, the second proof involves some type of, like, you know, they use some Kruskal-Katona theorem and, like, you know, did some convexity argument. And this paper is actually very clever and very short actually. Like, I would, like, you know, definitely recommend this paper. So in this talk, I'm going to, like, you know, sketch this proof because it's very short and, like, you know, you will have some insight into this type of problem. Okay, is there any question?
Does that the last theorem implies that this is true for all T because of the second?
Yes. So Chase plus 2, the result of Chase plus 2, this basically says that KTG less equals to KT second implication sign, like, you know, for all, like, you know, all the parameters, all possible parameter values. Like, of course t greater equals to 3 because we know that it's not true for t equals to 2, right? Huh? Any more question?
If you allow delta to go with n, then how big can it?
If you so I mean delta, I guess you like, you know, the interesting range would be to put, like, you know, some bound which where, like, t is at most delta. Is that your question? Sorry, t is at most delta plus 1, I guess. What did you ask?
Yeah, I'm asking if we will need any assumption on n, and the n needs to be big enough in terms of delta.
No. This is true for, I mean, this is clearly true even if n is, like, you know, smaller than delta, and, like, you know, it's always true, like, for all values it's true. Okay, so let me give you a proof sketch. So consider
What is the result? What is the first symbol after result?
q equals to 1. So n is globally defined as q times delta plus 1 plus r, and r is between 0 and delta. I mean, when I say globally means, like, you know, for the first part of that rock. For the second part, I think there will be no n actually. So yes, we can say it's globally defined. Anyway, so proof of 1. So let G be a graph with maximum degree delta and a number of vertices n. We will do two cases. Case 1, the minimum degree of G is at most r minus 1. Okay. So in this case, we can do a simple induction. So K3G. So we have a vertex. Basically, there exists V such that degree of V is less equal to r minus 1. We can write this as the number of triangles in the graph after removing V. Like, you know, when you remove V, you remove all the edges incident to V, plus the number of vertices and number of triangles where V is a part of.
So you write G/V for just deleting V?
Yeah, like delete V and also delete all the edges incident to V. Are you not happy with that? Is there a better notation you want to?
Like slash is like contraction. I mean,
Like this?
that
Like
would be
this?
better.
Oh, yeah, sure. Okay. I mean, I never use the other direction slash, so like both of them are same to me. Okay. Anyway, so now we can use induction for this part, and that will give us, like, you know, Q times. Okay. Remember, Q is 1, so it's just delta plus 1 choose 3 plus r minus 1 choose 3, right? Because G minus V has, like, you know, delta plus 1 plus r minus 1 many vertices, right? Like this is n now.
What is K3V?
So K3V is number of triangles where where, like, you know, like containing V. Let's just write that.
So not in the one vertex graph V.
Right. Like this is not a graph technical. So this is the definition for this. Okay, yeah, that's kind of average of notation. Yeah, I agree. And so K3V is at most r minus 1 choose 2, right? Because the degree is at most r minus 1. And so this is basically delta plus 1 choose 3 plus r choose 2, r choose 3. So this case was easy. For the other case, we are going to count the number of copies of this. So what I mean by this, we have three vertices UVW. UV is an edge, VW is a non-edge, and UW we don't know. It can be either edge or non-edge. Okay, so we want to count the copies of this inside G. Okay, so from the perspective of V, you can choose U in dV many ways, right? And from the perspective of V, you can choose W in n minus 1 minus dV many ways, right? And you sum over V, so this is the total number. And we now count in another way. So for every 3 vertex chosen in the graph, they will induce one of these these 4 graphs. So I'll just draw quickly. So, and something like this, right? And now let's see how many copies of this we get from each of them. So this one contributes 0 in this sum, right? Because this doesn't have any such copy. This again 0. This has 2 because we can pick V as either as this vertex or this vertex, and again this has 2. Okay. So now the number of this copy, we can write it in the following way: 2 times n choose 3, which is the number of ways you can choose 3 vertices, minus the number of triangles in G, minus the number of independent set of size 3 in G. You happy? So they are equal because we are counting the same object. G bar, right? Thanks. Right. Okay. So what do we get? We get something like, if you like rewrite, you have like k3g plus k3g bar. This is something like n choose 3 minus half times sum v dv times. So n minus 1 is just delta plus r. So remember, in this case n is delta plus 1 plus r. So we have delta plus r minus dv. We have this, right? And now we use k3g bar greater equals to 0. This tells us this k3g is less equals to this quantity, right? And because we are using this k3g bar greater equals to 0, this only works when q is 1, because if you look at the extremal construction when q is 1, that's just k delta plus 1 and kr, right? No independent set of size 3. Okay, so that's why, like, we cannot hope this argument to work for q higher than 1. Okay, because you, in that case, you will have, like, C size independent set anyway. So then, like, this is just some computation. So if you have k3g less equals to this, and we know dv is between r and delta. So this expression is just like, you are multiplying two numbers whose sum is fixed. So if you want to, like, minimize, then you have to, like, put them as apart as possible. So this is just delta plus 1 plus r choose 3 minus half times delta plus 1 plus r times delta r. Yeah? And now, like, some elementary computation will show that this is delta plus 1 choose 3 plus r choose 3, which I'm not going to do. It's actually not that bad. You can do some double counting argument to do that, but so that is the proof of this. It's like, very elegant and simple. So this is a very nice trick. Any question? It's actually strict inequality. So like for this part, you like, you can argue, like, you don't even have any extremal graph from this case. So all the extremal, so which is true, by the way, like in any extremal graph will actually have minimum degree at most r minus 1. Yeah.
The number of these things is greater than equal to 0.
So this is greater equals to 0.
Oh, okay.
Because, like, this is like your number cannot be negative, right? I mean, the count should be, like, non-negative.
You wrote the k3g more that.
Right? From this, I wrote from this.
Where does n choose 3 go?
N choose n is delta plus 1 plus r, actually. I'm sorry.
Oh,
Because when we are proving this, q is 1. Like, I'm just doing the q equals to 1 case. Exactly. Okay. Maybe I should have written that before starting the proof. I thought, yeah. So q is 1 here. Any more questions? So now we will move our discussion to the edge analog of this problem. So I'm debating where I should write. So maybe I just erase this part, right? Or let's just write that. Let's complete or the so edge analog. So in edge analog, what we do is fix number of edges instead of number of vertices. Okay. So the problem is still the same. You have a graph whose maximum degree is delta. Now instead of having n vertex, we fix the number of edges. It's m. Then maximize the number of copies of kt. Okay. So before going to that, let's ask a simpler question. If we don't have the maximum degree condition, then maximize number of kts in a graph with m edges. So again, like, the natural guess would be to like first have a clique with like at most m edges, and let's say we have like some kr, and then like remaining edges just attached to a single vertex, right? That would be a natural guess, and that is indeed the right answer. So first write m as like r choose 2 plus s, where s is like I guess less than r. Yeah, so you can like basically write every integer uniquely in this way, and then this graph is indeed the graph which maximizes number of KTs, and the literature calls it cliques graph on m vertices. We'll denote it as m, so I'll write it cliques graph on m vertices. So the name comes from like this there's some colexographic ordering on natural number set, and like this graph comes from like something like that. So so this let's write it as a proposition. KTG is at most KT Q, there is no Q, KTLM for all M edge graph G. Okay, and this can be seen as a consequence of Kruskal-Katona, but like this proving this is actually really easy. There is a more like way more general statement. Okay, so now if I ask this problem and restrict the maximum degree as well, what will be the natural guess? Right, exactly. So we first have like copies of k delta plus 1. At the end we have like this cliques graph. So our guess will be something like this, and at the end have this, right? So let me now tell you what is known and what we did in this regard. Okay.
Do you say that proposition, do you have restriction on t? Is t at least 3, or is it?
I mean, t is definitely at least 2, and I mean for 2 it definitely is true, because both of them have like same number of k2. T is like, yeah, you can you can say t is at least 3. It doesn't matter, for t is 2, it's true anyway. Okay. So also note one thing, when we fix number of edges, we can assume that there is no isolated vertices in the graph, because it doesn't, like for this problem, like having isolated vertices doesn't do anything for number of KT or number of edges, right? So Kirsch and Radcliffe, they proved the following, that for all graphs G with m edges and maximum degree at most delta, we have Kg. So remember, Kg is the total number of complete subgraphs, right? I defined there. I hope you remember. So Kg is at most K Q K delta plus 1 union K B. So I should write M now. Yes. So M is now Q times delta plus 1 choose 2 plus B, where B is less than delta plus 1 choose 2. Okay, this makes sense. So they proved this. So this is basically like saying that that graph is essentially like achieves maximum among all graphs with m edges. Okay, and So two things, if Q is 0, then this is already done by the proposition I wrote, right, by proposition, because even if you don't have the maximum degree condition, you know, like you have this collex graph, and for B equals to 0, this can be also proved by some simple argument, which I'm not going to say. It's basically you don't have this collex graph anymore. Anyway, what we proved is, and they of course conjectured that this is true for individual KTs as well, and we managed to prove that that is indeed the case. So I'm now going to give a rough proofs case of a small case of that. I'm sorry? Collex graph, yes. Right, thanks. That's the collex graph. Thank you very much. Oh, nobody noticed. Yeah, so this is the collex graph, because we have this k delta plus 1s, and then at the end we have this graph, right? Because the number of edge is fixed. So I'll give some proofs case for t equals to 3. So I should say that for this problem we couldn't get such reduction to t equals to 3, and it's probably I mean it might be possible, but we couldn't do something like this, and it some initial try suggests that it can be hard for edge variant. So we did for all t, but we basically did similar argument to t equals to 3, and it was just more complicated. Anyway, so I will write a series of lemmas, which I hope you believe. So if G is a minimum counter example, so what I mean by minimum counter example is just a counter example with minimum possible number of edges. Okay. Then G is connected. This is very believable, right? Because if it's not connected, then you can induct on connected components, right? Second lemma, same statement. G is a minimum counter example. Then G does not contain edge cut and edge cut with at most r minus 1 edges. In particular, minimum degree of G is at least r. So what I mean by that is if you have some edge cut, it is this edge cut should have at least r edges basically. Okay, that's all I meant. Good question. What is r? So r is I basically briefly said here. But in here, B is r choose 2 plus s, where r is sorry, yeah, this is right. S is at most r. I mean, as I mentioned, you can write B in a unique way like that, and this r is this r. Okay. Okay, so let's actually prove that, because it's not hard to prove that. So let's just name this is lemma 1, let's say lemma 2. Proof of lemma 2. So suppose you have a edge cut. So suppose the statement is not true, then there exists an edge cut B, like edge cut with like beta which is less equals to r minus 1 edges. Okay. So consider this graph G prime, which is G minus Are you not happy with this notation again?
The other way would be bad.
Okay, so we have this graph G minus B. So G prime clearly satisfies this statement, right? Because G is the minimum counter example. Okay. So and what can we write about K3G? We can write that K3G is at most K3G minus B plus beta choose 2. Let me explain this. So the triangles in G, they either don't use any edges in B, which falls in this category, and it can use some edge in B, right? So if it use, like if some triangle in K3G uses an edge in B, then it should use exactly 2 edges, right, in B, right? And so beta choose 2 will be an upper bound on the number of triangles using edges in B, right? Because you can like select beta choose 2 many pair of edges in B. Okay, and we can use like induction on this. So what is the number of edges in G minus B? This is just Q times delta plus 1 choose 2 plus R choose 2 plus S minus beta, right? So you can split into 2 cases. I will just show you one case. So if beta is less than S, then we can say that K3G is actually less equals to, so what will be this? This is just the number of triangles in this structure. Where is the structure? In this structure. So so using this, we can write Q times delta plus 1 choose 3. That's the number of triangles in the K delta plus 1s, and then we have plus R choose 3 plus S minus beta choose 2, right? And then plus we had this beta choose 2 term, and now we all know that this is at most S choose 2, right? So we have shown the assertion for this case, and case 2 is similar, which I'm not going to do. Right. So case 2 will be something like beta is something like this, right? Yeah. So we have proved lemma 2. Now, what is a natural way to count number of triangles in a graph? So now this is like proof, like attempt of proof of this statement. Right? So K3G is at most 1/3 summation V dV choose 2, right? Because every vertex can participate in at most dv choose 2 many triangles, and like every triangle can be counted at most 3 times. So this is an upper bound on number of triangles. And now what do we know about this dv's? Okay, so we know a lot actually. So summation dv is fixed 2 times m, like m is the number of edges which is written there. What else do we know? We also know that the degree dv should be between r and delta, and we also know the number of vertices is at least q times delta plus 1 plus r plus 1. Why so? Because if not, then use the vertex statement and we are done. So the vertex statement says if the number of vertex is like at most q delta plus 1 plus r, then the number of k3 is bounded by the number of triangles here, right? And which is definitely less than the number of triangles you can have here, right? Because like this so this r is same as this r now. So you have basically you have this extra, possibly some extra triangles because of this part, but everything else is there. So we can assume this. So I will write in bracket else use vertex analog basically. So we have this. So now we can treat this as some like just algebraic equation, and we can write it as 1/3 summation I equals to 1 to, let's say this is n, this number is n, equals to 1 to n di choose 2, and summation di we know, and each di's are between r and delta, right? And we can optimize this like we this function x choose 2, I is like the indices, it's going from 1 to n. So like there are like n vertices basically, and
di is just the degree.
di is just a degree. Yeah, I'm just writing this way. Just forget about the graph structure. Now like look at di as just pure number. Like just look at it as an algebraic equation. Okay. So this thing, this expression, like this is like sum of convex functions. X choose 2 is convex when x is greater or equals to 1. So you can like maximize this quantity by setting all the di's to like extreme values, like either set all of them to delta, like basically set all of them to deltas and r's basically, because you have like this sum restriction as well. So that will also like play a factor. So this can be like done, but of course not surprisingly this doesn't give us the right answer, because we are definitely overcounting here. So what kind of overcount we are getting? So if we have a structure like this, let's say this is v and this is a non-edge, then we are definitely counting this inside this bound, right? Summation dv choose 2, right? So we should like we should not count these copies, right? This is like induced k12. Let's first have some idea how much overcounting we could make here. Okay, so if we look at this extremal graph, note that this extremal graph actually has these copies of induced k12, right? And that's because of this residual part. In the Collex graph, if you look at it carefully, so we have this kr, and this vertex has s many s neighbors in this kr. Then if you pick this vertex, a vertex from its neighborhood and a vertex which is not adjacent to this guy, then this forms a copy of k12, right? This is like, let's just keep names. So this is v, this is u, and this is w. Okay, so then u v w forms a copy of k12, and how many such copies can be there? s times r minus s, right? That many. Now, so this is just a rough estimation. This is like, you know, not part of proof. Like I'm showing, like, you know, how bad this upper bound can be. Okay, so this is like, you know, in the order of r square, right? So in some sense, if we can, like, you know, subtract a factor which is, like, you know, quadratic in r, then we have some hope to get the tight bound from here, right? So we do that in the following way. Better bound so K3G is 1/3 summation dv2 minus 1/3 mu g, where mu g is number of induced K12 basically, right? Because every time we have this, we are adding a 1/3 factor here, right? Is there any question? Yeah. So now we'll prove this lemma, and essentially this lemma, like let's call it lemma 3, and this lemma, if we use this lemma 3, this basically give us the right bound. Okay, like right bound means, like, you know, just the number of triangle in the extremal graph I drew over there. So lemma 3 says basically if G is a minimum counter example, then mu of G, so mu of G is this number of induced K12 is at least r square. Okay, let's prove this. So here we are going to use this. Basically we have proven this fact that, like, you know, all the edge cut should have at least r edges. So pick a vertex u, look at its neighbor nu, and suppose this is the rest of the graph, and we know this is non-empty. Why? Because, like, remember, like, q is at least 1, and we know that number of vertices in the graph should be, like, you know, more than delta plus 1, and this is at most delta plus 1, right? Because u has degree at most delta, and we know that there are at least, like, you know, r edges, like, you know, in this edge cut, right? And suppose this is v and this is w, then uvw induces K12, right? So basically for each u we can get at least r copies of induced K12 of the form uvw, right? So then what is the total number of induced K12? That is, at least for each vertex you are getting at least r, and how many total vertices are there? That is at q delta plus 1 plus r plus 1, right? Which we proved, like, which we said here. So and times each of the induced K12 uvw can be counted at most twice, exactly twice actually, because it will be counted once from the perspective of u, another time from the perspective of w, right? When we draw this diagram, so we have a factor of half, and I mean, you can see this is at least r square, because, like, you know, q is at least 1 and delta is definitely at least r. So that's it actually. So we have proven the lemma 3, and this basically gives us this negative factor well enough so that we can reach the right bound. Basically that's the gist, that's the main idea. And of course, as you can see, when t is greater than 3, like, you cannot do this straightforwardly, right? You cannot just avoid induced K12 or something like that. Like it was like more effort compared to this. And yeah, it would be also nice to see if such reduction can be done for the edge problem, like it was done in the vertex version. Then just this proof would imply for all t if you can do this reduction, hopefully by some simple argument. Yeah. Oh, because so this so in this diffuse 2 you are counting this as 1, right? And there is a 1/3 factor here, so you are basically counting this as 1/3 in the summation, so that's why you have 1/3 factor there as well. So in this induced K, actually you are so this is counted only from the perspective of V, not in the perspective of this. That true, but like you are, so how many times you are counting this structure in this sum? Like think about that. You need to subtract that, right? And you are counting that 1/3, right? So like if you are confused, you can, so whenever you write some expression and you have overcounted, just see each of the things which caused the overcount, how much that is causing in the overcount, and just subtract that factor, right? So any more question?
So since when B is 0, then it's just trigger case that you don't care.
So basically this B0 case, those things are also important. Like I have used numbers like r-1, so then basically so for that, like we need to first make sure B is 0, for those corner cases.
So you're assuming so far that B is
Yeah. So maybe I will mention some problem you can think about if you want. So this is a big open problem in the literature when T is tree. So this notation just denotes the maximum number of edges in an n vertex T free graph. Okay, this is not even asymptotically known for all tree. And of course, I mean, if you don't know this, probably it's it's pointless to think about this. But people have studied this and they proved if some there is some conjecture on this, and if that is true, then some asymptotic value of this is also true. People have proved such things. So now maybe one can study such problems when number of edges is fixed. I'm sorry? I'll write it. Maximize number of KT in an n-vertex T3 graph. So, for example, the vertex version here deals with the case T is K1 comma delta plus 1, right? So it is also for graphs like path, these results are exactly known, but in general this type of problems are hard. So of course when you think about general problem, of course the arguments will be very different. You can all you try to prove some asymptotic result first, right? I mean for this simple cases you can hope for exact result. For the general case we can only hope for some asymptotic results first. Okay, is there any question?
Any questions?
Then I have one question. So you already so why is the bound of the kg, not kt, is known earlier than the kt? Right?
Oh, I mean,
Is there any
this is easier, right? I mean, if you know this, then like take summation over t, and then this will imply the previous result, right? So this is a weaker version. So so like that's why like some weaker result was known before, and then we strengthen it.
There, I mean, what is known for graphs with every two vertices have degree sum at most delta?
So you're like this is some type of like or type of condition, right? Something like that. I don't know. I haven't like thought about such things. So every vertex, the sum of every like every two vertices, sum is at most delta. Yeah, that's like perhaps one can study such problems.
I also wonder if there's an graph analog of this kind of.
I mean, to my knowledge, I am not aware of any hypergraph analog. No.
Can you say a few words about proof when t is bigger than 3?
Oh, I mean, so in that case, like, so we somehow have to see, like, from a vertex point of view. So suppose this has like some, this is u and this is the neighborhood nu. So every copy of kt corresponds to some kt minus 1 inside nu, right? So we kind of relate like the number of kt minus 1 here inside the neighborhood with like number of missing edges in the neighborhood. Like we try to relate them and like do some inequality, like that's so basically we kind of like do something like this, but like it was very indirect. Yeah, it's something like that.
I was just going to ask which trees have been studied here.
Oh, I think for this classical problem, I think people know answer for some caterpillars and like some like some very specific trees. I mean any I mean this is like it's very easy. So okay, if I remember correctly, so if like say tree has like t vertices or t edges, doesn't matter, and it's very easy to prove a bound in the factor of 2 basically. So I think the conjecture is something like you have nt over 2, right? Yeah, but that is for, that works only for when t is large enough, right? Something like that.
So allegedly it's proved already in the
But they haven't published.
That is t large enough, right?
T
is the number of
Yeah, so t is for I think for like constant t, it's probably like we know nothing, right?
Like if the tree is diameter at most 4 or something,
Yeah,
it's already very complicated. It's 30 pages or something.
Yeah,
I think they have
like this.
they have never written up the proof.
But for sufficiently large trees, there's a result claim.
So they claim that it is now asymptotically for if the size of the t is big enough.
And what is the asymptotic behavior? Is it they claim?
So
Half of
you basically have like this can be one of the structure, I guess, like you have just kts, union of kts. So count down. I mean this is
So
probably there can be more structures, but like asymptotically this should be like same as that. This is conjectured. Yeah. This is definitely conjectured. This is like some Aedis Galli, Aedis and Sauce, right? Aedis and Sauce, right? So, and it's very easy to prove an upper bound of NT basically. It's very easy. Like, yeah, the like it's conjectured to be this NT over 2, and it's very easy to prove less than NT. Like the argument is also very simple because so if it is yeah, so if you have a graph with average degree t, average degree 2t, if you have a graph with average degree 2t, then you have a subgraph of that with minimum degree at least t, and then you can embed any tree on that basically.
Yes.
That's the proof. Right? So.
So I guess that one natural generalization of fixing the number of edges, you could fix the number of small cliques.
That's also a possibility, and my guess would be it would go really messy, but it is a, so for example, for the standard Turan problem where you forbid cliques, that kind of problem has been studied. So you say that you have at most some number of triangles and you avoid k-tens, then what is the maximum number of k5? Stuff like that. And it follows from some I think some general result by Jacob, and so such things can be studied here, I guess. And I mean, so it's very easy to actually come up with a graph which will probably be the best, and that would be probably the best. But this kind of argument can get really messy. It's a good question. I mean, my guess would be try to make it as badly connected as possible. Perhaps removing one is there and adding something like that. I would guess, but I'm not sure if that would be an interesting problem.
What if we want it to be highly connected?
Any other questions? Okay, let's take the speaker again.
Okay.